Hi, so I guess another another snow day. So this seems to be this year there'll be more online lecture than during the pandemic. All right, so let's look at defining holomorphic functions via integrals. So this is subsection 341. And we've sort of seen a little bit of this, but let's see sort of the general statement. Let me move myself a little bit here. So suppose that you have, so this is the general lemma, general kind of statement that we're interested in. I mean, it could be, other ways, but, this is the one that we'll need, the one, in sort of the most generality that we'll need. So suppose that U is open, right? Some open set in C. And suppose that we have some continuous function of two variables, one complex, one real, right? Defined on U, and the little interval, you can, for all practical purposes, just make it 0, 1. Make it a closed interval. It's a continuous function. So continuous function of those two variables. So really, it's a continuous function of three real variables, right? X, Y, and T, if you want to think of it that way. Right, and suppose, so this is the only other thing that we're gonna, assume about it. So that for each fixed t, right? So fixed the second variable, the variable in 0, 1, the function that takes z to c zt is holomorphic, right? We're not saying anything else about this. Just that when you fix a t, you get a holomorphic function, right? For every fixed t. We're not really saying how these are related to each other, except that c is continuous as a function of z and t, right? So those are the hypotheses. And then if you integrate out the t, so if you integrate from 0 to 1 in the t variable, right? So then you get, right, I mean, you're left with a function of z alone, right? So then that guy is a holomorphic function. Well, of course, it's defined on U. So for each z in U, right, you get some number, right? And this is a holomorphic function, right? Seen one example of that, but this is the more general version, right? So, and there are two sort of kinds of proofs of this sort of results. When you want to show that something is holomorphic. So one way is to use Moreira, and the other way is to use the Cauchy-Riemann equations. So let's first do the Moreira version, right? Let's prove this using Moreira's theorem. And there's gonna be some exchange of limits involved, and the exchange of limits that we're using is Fubini, right? And then we're gonna use Cauchy's theorem. All right, so take T to be a triangle, and again, this means that the entire solid triangle is in U, right? So T, including the boundary, including the inside, everything is in U, right? Then let's integrate around the boundary of this little triangle, or little, big, I don't know, whatever triangle it is, z, right? And we're trying to show that this is 0, because then we can apply Moreira, right? So if this was for every such triangle, Moreira says that H is holomorphic, right? So we're trying to show that this has to be 0, no matter what the triangle is, as long as it's just a triangle in U, right? So let's just write down what that is, right? Well, let's write down what H is, right? So H, I mean, that's just this expression. That's the definition of H, okay? So now what we have is two integrals, right? This integral over here, right? I mean, it's really a sum of three integrals over intervals, right? I mean, underneath, there is some sort of a, maybe I shouldn't call it t, but some sort of an interval tau or whatever, some parameter, right? That runs over those three lines. So really, if the idea is being able to swap the, this one-dimensional sort of calc1 type integrals. When can I swap those? When can I move this, this t, this boundary of t guy, right? When can I move inside? And we know when we can do it. I mean, Fubini's theorem tells you when we can do it. Yeah, essentially, if you have Lebesgue theory, it's much more general. But in this case, the sort of the Riemann integral version of Fubini. Well, if you have a continuous function of the two variables, yeah, you can do that, right? So because this C is continuous, we can just apply Fubini. And now, if you want to apply that, I mean, remember what the definition of this integral in there. We also have this dz, right? The dz has that has the derivative of the parameterization, right? But again, just apply it on every one of those three intervals, right? On every one of those three intervals, the derivative of the parameterization is continuous, right? So you can easily apply the most basic version of Fubini. And you could, if you want, you can apply a more complicated version of Fubini as well, of course, right? But that's what we're applying Fubini, right? So there's something to say, right? It's not you can't always swap the order of integrals, but most often you can, and definitely in this continuous setting you can. All right. Well, now this thing, right? So here the t is fixed, right? It's inside the integral. T is not moving. T is moving outside, right? So if I look at this expression, I'm really looking at it for any particular t. Now, for any fixed t, this is a holomorphic function, right? So this is where I'm applying maybe Cauchy-Gaussard or some other version of Koshi. This has to be, right? Another version of Koshi could be, you have a triangle, right? There's some neighborhood of the triangle, right, which is a star-shaped domain, right? Because the triangle itself is star-shaped. So you could do that. So there's a bunch of different versions of Koshi that you already know that you could apply to make this to say that this is zero, right? Cauchy-Gaussard says pretty exactly this, right? It was this exact hypothesis. So that's why I said Cauchy-Gaussard. So then you get zero. So we're just integrating zero, and we get that this guy is just zero, right? So again, Fubini applies as the integrand is continuous, right? And again, you wouldn't necessarily need continuity. You need some sort of a, since these are sort of integrals over bounded intervals, as long as everything would be bounded, it would be enough by the Lebesgue version. But we can use the simplest version of Fubini is good enough. All right. And so H is holomorphic. All right. So that's one proof, right? Let's look at the second proof. So this is using Cauchy-Riemann equations, and it's actually, this is the proof that, well, this is the kind of proof that we already did on the Cauchy formula, but it's maybe a little bit more subtle, although it might be. This would really be the way that I think of it, but it is a bit more subtle. We'll get to the subtlety in a moment, right? So basically, the idea is you apply the Cauchy-Riemann equations, and we can just apply the Wertinger derivative to it, right? We just integrate with differentiate with respect to z bar, and check that that's zero, right? So let's try to do that. here we try to, really so far, it might be a little bit, we're going a little backwards. So, I'm going to write out what I'm doing, and then I'm going to justify it. But it needs, all these things need justification, right? I mean, a priori, it's you need to even justify this thing, right? I mean, I don't know that this is differentiable in any way, right? So it's sort of going backwards, but we're going to justify it, everything, right? So it's important to note that. So we can take the integral, take the derivative past, by Leibniz rule, right? And yeah, can we? But yeah, let's suppose that we can. Let's suppose that this works, right? Suppose that this is possible. If we can apply the Leibniz rule, then this really is differentiable, and then we really do get that the derivatives is zero, right? Okay, so then this is zero because C is holomorphic for every t, right? Now, we're really passing the x and the y derivatives underneath, and well, we know that those exist, but we don't know that they're continuous, right? So can we actually apply Leibniz, right? I mean, if we assumed a little bit more, then everything would be fine. But we only assumed that this is holomorphic for all t. We didn't say anything about what happens to the partial derivatives. I mean, you know that for any fixed t, the partial derivatives are continuous, right? Because it's a holomorphic function. It's infinitely differentiable, right? But we don't know if those are continuous as you move t, right? So a priori, this doesn't quite work yet, right? I mean, you cannot just apply Leibniz here, right? You need a little bit more, right? I mean, if we assume that the x and the y derivative, right, the real and imaginary part, and hence this guy, if those were continuous functions, so basically we're almost assuming that c is c1, well, except we're not saying anything about the t direction, but essentially, right? But the point is that we'd have to assume that these guys over here, we'd have to assume are continuous function not of just z, so not just x and y, but also of t, so of the three variables x, y, t, right? Or maybe z and t, right? If we had that, then this would be a perfectly valid argument, right? Because that's exactly what the Leibniz rule gives us, right? I mean, you can do this in more generality, but the point is also, I mean, we only know, right? I mean, this guy being zero implies holomorphic only if h was actually c1. So we had better have c1, right? And so Leibniz does tell us that as long as these guys are continuous, right? But this is actually, an interesting consequence of the Cauchy integral formula, and it's an exercise in the book that you don't actually need to assume that these are continuous, right? And, if we were talking about anything other than holomorphic functions, you would need to do that, right? But in this case, because you have Cauchy's integral formula, so in Cauchy integral formula, you write down, for example, the derivative, right? So the integral formula for the derivative, right? The derivative basically gives you these guys, right? I mean, it gives you the z derivative, which you can identify with the Wertinger we're taking a derivative of this function, right, for any fixed c, fixed t, sorry. So it's so that gives you the x and y, right? And in the Cauchy integral formula, all you need is the values of the function, right? So because you have the values of the function and sorry, why did I have? Well, anyway, the values of this function, right? It's continuous. You actually get that these guys are going to be continuous also in t because of the continuity of this expression in t, not just in z, right? So, well, actually, the continuity in all variables, right? So this is a consequence of the Cauchy integral formula that you actually only need to assume this is holomorphic, and you will get that these guys are actually continuous, right? And so you will get that H is C1. Well, and then you can also, you can write down this entire computation, right? So okay, so now we're done, right? So it's a bit more subtle. If you had, if you assume a little bit more, it would be less subtle, right? So, for example, if the function under the integral is c1, like it was when we did this for the Cauchy integral, right? It was c1, right? So we didn't need to, work with this level of generality. And you can see that the Moreira way of thinking about it is actually, also very good because it was, less subtle than this. You didn't need to worry about, well, all these hypotheses that you need to satisfy. All right. So let's look at a corollary. So this is basically just rewriting it for a path integral. So instead of an integral from 0, 1, right? Yeah, you could just have an integral over a chain, right? That's the only thing here, right? Suppose that I have this chain, right? Whatever it is. So it's a, some formal sum of a bunch of paths. Piecewise C1 path, right? That's how we defined it. And we integrate. We have a function of two variables, right? One of them varies over u. The other one varies just over the path, over this chain, right? So over the where those paths are defined, and suppose it's continuous there, right? And holomorphic when restricted to z. Then we have that this guy is holomorphic, right? So, right, nothing new. It's basically just, using the lemma, right? But it's sort of the way that we wanna think of it. Let me move myself back up here. So that's probably the way that we want to think of it. In a bunch of these applications. So that's why I'm writing it. So for example, we can define the Cauchy transform as something taking boundary values into a function defined inside. So here we're doing it on a disk, right? So we have a disk and the boundary of the disk. So if I have a continuous function on the boundary, then we have the Cauchy transform, right? Which is just this thing. It's a function of z, right? It's a function of z on the disk, and right, that's what it is. Now, if f was really the boundary values of a holomorphic function, then the Cauchy formula would tell you that CF is actually equal to F, right? But here, F is just some continuous function defined on the boundary. We have no clue necessarily when we define this, what sort of a function it is. Did it come from a holomorphic function? Did it not, right? We're only assuming that it's continuous. You can assume a little bit less, but the way that we set up, we're assuming it's continuous. And so we define this this function, right? And basically, this corollary over here implies this corollary over here, saying that this CF is holomorphic, right? So given any continuous function on the boundary, then you have this is your psi, right? That's this guy over here, right? I have it in two variables, right? So maybe the W over here is the zeta over here, right? And so that's holomorphic. Now again, if we don't know anything about F, the values of CF and the values of F may have nothing to do with each other, right? F is only defined on the boundary, so you can't talk about what it is inside the disk. But even as you're getting close to the boundary, right? So as you evaluate CF closer and closer to the boundary, this Cauchy transform might have nothing to do with the values of it. It might be very far away from it, right? So it's not like, F is going to be the boundary value of CF, right? Well, it would be if F was holomorphic in a neighborhood of the closed disk, for example. But other than that, you don't know, right? But we know that it is holomorphic, right? CF is holomorphic. Now, it gives, maybe this is not as useful as it may seem, but it gives a converse to Cauchy's formula. Cauchy's formula should only work for holomorphic function. It might be a little obvious, but right. But it's basically, because we know that the Cauchy transform is always holomorphic, right? So if we have a continuous function on the closed disk, right? And we have that F is equal to it's to the Cauchy transform on the boundary, right? So the boundary values of F. So if this is true for all z in the disk, then F inside is holomorphic, right? And well, the point is that this guy is holomorphic, right? So if this is actually equal to this, then it's holomorphic, right? That's basically the idea. So we have, it's just, right, kind of obvious, but so there you go. So Cauchy's formula can only work for holomorphic function. It's basically an if and only if. But generally, you wouldn't really apply it this way, right? Because usually you apply it by, I know this function is holomorphic, so therefore I have the Cauchy formula, right? If you have the Cauchy formula, you already know a lot about the function, basically. So, all right. So that's it for this subsection. So we'll have one more for today. So let me stop this.